Good everyone, my name is Graphics. If you look at the front of your screen, there's a problem that is displayed there, and that is based on hydraulics and hydrology, which is an aspect of fluid mechanics. Now, the question goes like this: it says, for the frictionless siphon shown, determine the discharge and the pressure head at A and B, given that the pipe diameter is 200 millimeter and the nozzle exit diameter is 150 millimeter. Now, the first thing you do is to write out the data given. Now, the data given here, we say the diameter of the pipe is 200 millimeter. So we call that T subscript 1. So that is the entire diameter of the pipe, which is 200 millimeter. And when you convert to meter, you have to divide by 1000. And that will give us 0.2 meter. Automatically, we are given also the nozzle exit diameter. So this is telling us that the exit of the pipe is smaller than the entire pipe. So it is a nozzle, so it is reduced, and we call it D2, D subscript 2, to be equals to what? 150 millimeter. Now, if I convert it into meter, I will divide by 1000 and I'm going to be having 0.15 meter. Now, you see we're using 1 and 2 just like it is shown in the diagram like this. You see here we have 1 and here we have 2. Now, we calculate also for the area. So, area of the pipe is given as A1, and that will give us as pi d 1 square over 4. Because since we are considering section 1 of the pipe, we will use d1. So when you put your data, d1 is given as 0.2. So 0.2 square multiplied by pi divided by 4 will give us what? 0.0314 meters square. So that is our A1. Now, we'll look for A2 also. A2 is giving us pi d subscript 2 square over 4. And this will be giving us pi multiplied by d2 is giving us 0.15 square all divided by 4. And doing our calculation, we'll be having A2 to be 1.0171 meter square. Now, since we've written out the data, the parameter given, the first thing we have to do here, according to the question, is that we should calculate for discharge and pressure head at A and B. So I'll start calculating from discharge. Now recall, we know that discharge Q is given as what? The area times the velocity. Now since discharge will be occurring more at the exit of the pipe, which is at the nozzle, so we're using Q2, that is discharge at section 2, is equals to the area at section 2 multiplied by the velocity at section 2, right? Now we're looking for the discharge. We only know area, we don't know the velocity. So now we'll term that equation 1. So we move to the next level, calculating for what? Velocity. Now, how can I calculate for velocity is by applying our Bernoulli equation. So we apply Bernoulli equation at both section 1 and 2 of the pipe, right? So Bernoulli equation is telling us that the pressure head, which is giving us P1, which is giving us P over rho G, plus the kinetic head, which is giving us V1, that is V square over 2G, plus the potential head giving us what? Z is equals to C constant. But since we're not dealing with two sections, we will not say that what? The P1 over rho G plus the P2 plus the V1 square over 2G plus the Z1 is equals to P2 over rho G plus V2 square over 2G plus Z2. So the left hand side and the right hand side, just because we have two sections. If we have three sections, we'll continue that way. So this is what we have here, right? So what we'll do here is we'll start. Now, if you look at this diagram very well, you will discover that at section 1, the siphon is just dipped into the liquid, right? Now, dipping into the liquid, you only have one thing that can make the liquid rise there, and that is capillarity due to the surface tension. So the water will just move up. There is no pump. So in that place, the velocity, there's no velocity. So we say that our V1 is so small that it's negligible. So we say V1 is 0. Now, similarly, if you look at it on the surface, the only that act on that surface is just pressure, right? It's a pressure, atmospheric pressure. So we say that atmospheric pressure since is equals to the P, the pressure there is equals to atmospheric pressure. We say it is equals to what? 0. Now, if you equate out the pressure at the both side, we discover that at state 2, the pressure there also is there's no pressure because since velocity is high, means pressure will be what? Will be low, right? Now, we will now say P2, the pressure head at section 2 and the pressure head at section 1, they are all equals to what? 0. So in applying it, our Z1 will now be equals to V2 square over Z over 2G plus Z2. So we have it. Now if you make V2 square over 2G instead of the formula, we'll be having Z1, the Z2 will move to the other side, will be subtracted by Z2 equals to V2 square over 2G. Knowing fully well that V2 square over 2G is given as the kinetic head or the kinetic energy. Now, if you look at the diagram carefully, Z1 and Z2, this is Z1 from here, this is Z1, right? And Z2, this is the height difference there. So Z1 and Z2 is just given as what? 1.22 plus 0.125. That's what we have there. Is that okay? And that will be given as what? V2 square over 2G. Now when you add 1.22 plus 0.15, you'll be having 1.37 equals to V2 square over 2 times 9.81. So 9.81 is the gravity. Now when you do your needful, if you cross multiply, you'll be left with 1.37 times 19.62, which is gotten from 2 times 9.81 equals to what? V2 square. Now, if you make V2, this is the formula where the square goes to the other side, your V2 will become what? The square root of, when you multiply 1.37 times 19.62, you'll be having 26.87. Now, if you look for the square root of that, you'll be having V2 equals to what? 5.18 meter per second. Now, we're going to have V2. So, we're now going to what? Input it into equation 1. So, substitute V2 equals to 5.18 into equation 1 above. So our discharge Q2 will now be equals to what? A2 times V2. Q2 will now be equals to what is the A2? A2 is giving us 1.0171 times the V2 is giving us 5.18. So when you multiply both of them, Q2 will now be giving us 0.0915 meter cube per second. So that's our discharge at the exit of the nozzle. Now we've done that. Now the next thing we are going to do here is to calculate for the pressure head. Pressure head at A, that is the next task. So what will you do? Look at, we will apply Bernoulli equation along the stream of 1 to A. Look at the diagram very well. So we are attacking, because for you to use the Bernoulli equation, you need two sections in case of situation like this. So along the stream line 1 to A, from here to here, right, on this diagram. So we'll start. So at the left hand side will be for 1 and the right hand side will be for what? For A, right? So we say that the pressure head at 1 plus the kinetic head at 1 plus Z1 plus the potential head at 1 is equals to the pressure head at A plus the kinetic head at A plus the potential head at A, right? So this is how you write them. So if you look at the diagram very well, we will know right from the beginning that the pressure at section 1 is 0. I explained it earlier, and the velocity at section 1 is also was 0. So when you apply this into the above equation, you will discover that Z1 will be equals to P subscript A over rho G plus VA square over 2G plus ZA, right? So this is what we're having here. So from here, if you make your kinetic head the subject of the formula, you're going to be having your Z1 minus ZA equals to P subscript A over rho G plus VA square over 2G. So when everything go to the other side, you know your Z1 minus ZA. Let's see. We have Z1 minus ZA. Now look at the diagram very well. My Z1 at this line here is a reference line to the surface of the water. We see it is 0. The way I'm moving up to ZA is increasing, so that is what ZA is what 2.44. So 0 minus 2.44 will still give us minus 2.44, right? Equals to P subscript A over rho G plus velocity square over 2G at section A. Now if I make my kinetic head the solid of my potential head, the solid of the formula, because that's what we're looking for, we're going to be having minus P subscript A over rho G is equals to minus 2.44 minus VA square over 2G when VA square go to the other side. So that's my equation 1. Now from where we are, but we know that the discharge at A is equals to area at A times velocity at A. So our discharge at A is equals to the discharge at section 2. If I look at our diagram, this is A and this is 2. So when the liquid is falling, it falls with the same speed as that of what? Of section 2. So the discharge at this straight line between they are what? They are the same, right? So we move forward by saying that QA is equals to what? Q2, which is 0.0915 equals to the area at A from our parameter given as 0.0314 times the velocity at A. So if you make VA the set of formula, the VA will be given as what? 0.0915 divided by 0.0314. So the VA, V sub A will be given as what? 2.916 meter per second. So the velocity at section A is 2.916 meter per second. Now you substitute this into what? Equation 1, equation 2 above, right? So these are equation 2 here above. So when you substitute in, we'll be having the potential head, which is given as potential head at section A was given as P subscript A over rho G is equals to minus 2.44 minus VA square over 2G. Now our VA square is given us 2.916 square over 2G, and the GG is 9.81, so 2 times 9.81. So this will now be equals to, when you do your calculation here, we're going to be having minus 2.44 minus 2.916 square is giving us 8.5031, and 2 times 9.81 giving us 19.62. So when you divide both of them, you'll be left with 0.433. So minus 2.44 minus 0.433 will giving us what? 2.87 meters. So we've gotten that. Now we'll go to the next one, that is the pressure head at A. Yes? So we want to do for the pressure head at B. So applying the Bernoulli equation along the streamline 1 to B, look at the diagram very well. We're going along the straight line 1 to B. Alright? So we'll apply the Bernoulli equation too. So the right hand side will be for B, the left hand side will be for 1. Right? So the pressure head at section 1 plus the kinetic head at section 1 plus the potential head at section 1 will be equals to what? the pressure head at section B plus the kinetic head at section B plus the potential head at section B. So this is what we have here, right? So just like we said, the pressure at state 1 is equal to 0 and the velocity at state 2 is equal to 0. So by the time you do that in two here, you're left with Z1 is equal to P subscript B over rho G, which is the kinetic head, the potential head at B, plus the kinetic head at B, which is V subscript B square over 2G, plus the potential head at B, which is ZB. So if you collect like terms, to be Z1 minus ZB is equals to P subscript B over rho G plus VB square over 2G. Now we know very well that the velocity at B is equal to the velocity at what? At A, and that is what? 2.93. So when I input it here, and my pressure difference, you look at my diagram, this is Z1 to ZB. Z1 to ZB is what? 1.22. Look at it. This is Z1 to this point here. The distance is what? 1.22. So this will now be equals to pressure head at B over rho G, as in PB over rho G plus 2.93 squared, because VB is 2.93, which is equals to VA, all over 2 times 9.81. Now when you divide both of them, you will be having 1.22 is equals to PB over rho G plus, if you divide 2.93 square over 2.2 times 9.81, which is 19.62, you will have 0.436. Now if you take 0.436 to the other side, you'll be having 1.22 minus 0.436, and which will just what? PB over rho G, that is the pressure head. So my pressure head will now be giving us 0.78 meter when you subtract two of them. So this is how you can look for the discharge, the pressure head at A and B. So if you have found this video helpful, please don't forget to click on the subscribe button, like, and also share.